This is the one that everybody hates. Um, okay, so we've talked about addition reactions. We've talked about oxygens, nitrogens, hydrogens adding. We combine some of them in reductive amination. Now we have to talk about the equilibrium. And this is kind of the dirty secret of carbonyl additions, that every carbonyl addition goes both directions. Right? You add stuff to the carbonyl, but you can also lose stuff from the carbonyl. And so I'm going to talk about this in terms of acetals and hemiacetals. This kind of equilibrium is incredibly important in biochemistry because what happens in biochemistry is enzymes and proteins and stuff control how much of every nucleophile is present. And if they allow enough nucleophile there, you get nucleophiles adding to carbonyls, adding to hemiacetals, that kind of stuff. And if they exclude them, then the hemiacetals and all of that kind of stuff stay stable. And so you'll see this kind of equilibrium happen all the time in things like biochemistry and all that, but it's kind of hard to grasp because we often think of chemical reactions only kind of proceeding in the one direction. And when we draw mechanisms and stuff, we kind of say, well, this adds here, and then this adds here, and then this adds here. And that's not really what's going on, especially in these kinds of carbonyl addition reactions. So we're going to take this video, we're going to talk about the equilibrium, we're going to go forward, backtrack, go forward again, talk about when reactions have completed and how do we make them give us the products that we want. All right, I think that was sufficiently confusing. So let's talk about if we go from aldehyde to hemiacetal to acetal. Right, so we've drawn out this mechanism before. This is one of those great big mechanisms. I'm going to, what aldehyde should I use? We'll just use propionaldehyde. And I'm just going to use methanol because I want to keep this simple because we're going to be drawing a lot of intermediates. Okay. So if we treat this aldehyde with methanol and H+, we know what's going to happen, right? We're going to get this H+ being added to the carbonyl. And this is just your standard Bronsted-Lowry acid-base reaction, right, back from the previous semester. And so we know that this is an equilibrium, right? So depending on which one of these things is more stable, right, the equilibrium will favor the starting material or the products, right? Depends on which conjugate base is more stable. Now we can bias this, right? If we use something like sulfuric acid is an incredibly strong acid. It has an incredibly stable conjugate base. And so if we use sulfuric acid, the equilibrium will favor the side where we have the conjugate base of sulfuric acid, right? So when we use H plus here, what we're doing is we're pushing this equilibrium towards this reactive carbocation because it also has sulfuric acid as its conjugate base. Now from here, we get methanol coming in and adding to the carbonyl, pushing electrons up onto the oxygen, right? And that gives us almost our hemiacetal, right? Now we've got CH3, oops. Now this is also a reversible process, right? It would be very easy for this group to be a good leaving group. In fact, that is a good leaving group, right? That CH3OH plus is a very good leaving group. And if that leaving group leaves, we're left with the carbocation, which is exactly our starting material here, right? And so this is the thing that's happening, is that every time we have one of these steps, the reverse step is also occurring. So sometimes methanol will add, and then it'll sit there for a little bit, and then it'll leave as a leaving group. And sometimes then the methanol will come back in and add again, and it will leave. Sometimes methanol will leave, it'll make the carbocation, and then that carbocation will lose H plus, and it'll go all the way back to the starting material, right? And so sometimes it's 2 steps forward, 1 step back. Sometimes it's 1 step forward, 2 steps back, right? There's always this kind of multiple steps are happening. The next thing is another Bronsted acid-base reaction. And so, of course, this is going to be another equilibrium. So depending on the stability of your conjugate base, right? And so the conjugate base in this case is a nice neutral hemiacetal. And so it's reasonable to assume that this might be favored, although it depends on how strong the acid is that's around, right? If you have sulfuric acid still in your reaction, sulfuric acid could easily add H plus, and send us back on this path, going back toward the starting material. Or sulfuric acid might add to, this is another acid-base reaction. Here we're adding H+, right? Sulfuric acid might add something to the other oxygen and make this thing into a good leaving group, right? So this is another equilibrium reaction. Again, we've got reactions going both directions. The H plus goes on, or if we go look at this backwards, the H plus comes off, right? Either way can happen, right? And so we get this kind of thing. And then what's going to happen next is we're going to have our leaving group leave. And so we lose OH2 plus, and that gives us our carbocation again. Again, I'm going to stabilize that carbocation using these oxygen lone pairs, and so you get this thing. And this is really the key step in any kind of acetal formation, right? Is this step here, because yes, this is an equilibrium, right? You could have water come back in if water adds to this carbocation. Again, that's a very reasonable thing for water to do. If water adds this carbocation, breaks the carbon-oxygen pi bond and pushes those electrons to make a lone pair on the oxygen, we get our other intermediate. So this is still an equilibrium, but we can manipulate this equilibrium so that there's only a very small amount that ever goes back that way, right? So how do we manipulate this equilibrium? This equilibrium is controlled by what nucleophile is present. Right? So if we have a whole bunch of methanol present and there's no water in our reaction, right? So we just use dry methanol where there's no water in it and methanol is the only nucleophile that's around. The only thing that's going to add to this carbocation is methanol. Right? Because that's the only nucleophile that's around. The only other nucleophile that's possible is this water molecule that just left. But again, this is going to be one water molecule in a sea of methanol molecules. And water and methanol they're equally good as nucleophiles. They're both neutral oxygen nucleophiles. And so one of them is not going to be more attracted to the carbocation than the other. So it really comes down to just a numbers game. Which one is there more of? And in this case, there's more of the methanol because that's how we set up our reaction. We put a whole bunch of methanol in there, and so the methanol is going to be the thing that adds. And of course, that's going to lead us to the thing that's almost our final acetal. But of course, this is a good leaving group, so this could easily leave and we'd be back at our carbocations. This is yet another equilibrium arrow here. And then the last thing we have to do is another Bronsted acid-base reaction where we lose H+. And if we do that, we get to our acetal. So notice that everything in this process is an equilibrium reaction, right? They're all going both directions. And the only way that we can really control what we get is we say, let's keep the amount of water in this reaction to a minimum, right? So if we keep the water to a minimum, that means that that one step in the middle only really goes one direction and only goes in the direction where the methanol adds, which is what leads us to our final product. Because, okay, so we can go forward and back as many times as we want across this kind of top row, but as soon as we drop down to this bottom row and lose water, we can't really get back over this reaction and get back to our starting material, right? So now we're stuck in this loop, and eventually we have a carbocation, we have a positive oxygen, or we have a neutral compound. Eventually, the neutral compound is going to be the favored product, right? So we kind of set up a roadblock here by not having any water present, and then let all the equilibriums kind of sort themselves out. Eventually, it's going to favor the neutral compound, and we're going to get the neutral acetal as our final product. Okay, so that's cool. But what happens if we add water to this, right? If we add water, what if we have more water than we have methanol? Right? Well, we can look at this and we already know, we don't have to draw a whole new mechanism. If we have more water than methanol, then this equilibrium is going to switch, right? And so now, if we have more water than methanol, right? Anything on the left side of this arrow, this equilibrium is going to push this direction because now water is the thing that's going to attack this carbocation. And so that means that once we get kind of past this arrow, we end up in this top row, everything's going to sort itself out. It's going to go to the neutral compounds here, which could be the hemiacetal, but is probably more likely to end up becoming just the original starting material. So what that means is that, okay, let me change slides here. If we start with a carbonyl, an aldehyde like this, and we treat it in alcohol with acid, so I'm going to use methanol as my stand-in, but it can be any alcohol, we get the acetal as our product, right? The equilibrium favors the addition of the nucleophile that is more present. But if we start with an acetal, and treat it with water and acid, it goes back the other direction, and we end up back at the aldehyde as our starting material. So this is kind of cool, although it's also kind of annoying, because what I've done is I've given you two mechanisms at once and just said the only difference between these mechanisms is which nucleophile is present, right? So if we run the reaction in methanol, it's going to favor the addition of methanol, so it's going to go from aldehyde to acetal. If we run the reaction in water, it's going to go from acetal to aldehyde. And you should draw out that mechanism, converting the acetal to the aldehyde, because it is basically this come on, let me change slides here. It is basically this mechanism, but in reverse order. So you start with the aldehyde. Instead of losing H plus, you add H plus. Instead of adding methanol, you lose methanol to go from here to here. And then at this point, right, instead of losing water, you're going to add water to go to here. Instead of adding H plus, you're losing H plus. Instead of losing H plus, you're adding H plus. Instead of, right, on and on we go. Each step is going to be the opposite, but you can draw this whole process out starting at the acetal and going back to the aldehyde. But the only way that's going to work is if you have more water present than whatever your alcohol is. And so this equilibrium is really important. I think it's kind of a hard concept to really grasp and understand, but what it really boils down to in its simplest form is what is the nucleophile that's most present and what does that mean for this mechanism? Because every step is in equilibrium, we can literally push this reaction to the right, to the products, or we can push it to the left, to the starting materials, if we switch what we have present in the reaction. I think that's kind of cool.